Hello everybody, welcome to the first Physics 331 video. What I'd like to start with is a discussion on the technique of lock-in detection. Lock-in detection is useful when you know the frequency of the signal you're trying to detect. In that case, what a lock-in detector is able to do is to extract even a very small signal of a known frequency from even when it's buried in noise containing frequencies of a wide range of values. And it's often the case that you do know the frequency of the signal you're trying to detect, because when you set up an experiment, it's often the case that you're driving the apparatus with some signal of a known frequency, and then you're looking for a response at that same frequency. Among the experiments that are available in Physics 331, there's several of them that do use lock-in detection. AC susceptometer is an example. Also, Faraday rotation is a second example. It's also possible to use the technique of lock-in detection in the speed of light experiment, for example, and the Hall effect measurement. So to begin, I'd want to just do a quick little review of an analysis of an RC circuit, because I think it's going to highlight some important aspects that we need to be familiar with for understanding lock-in detection. So I want to consider a series RC circuit. So what we're going to do is we're going to drive our circuit with an AC signal of some known frequency that we set. So there's our signal generator, and then we're going to have a series combination of a capacitor and a resistor and go back to the generator. So here's C and R, and what we can do is we can take our output as, say, the voltage across the resistor. We'll represent the input signal V in using a complex exponential, so it's going to have some amplitude and it's going to be driven at some frequency omega. So remember Euler's equation, e to the j omega t could be represented as cos omega t plus j sine omega t. So this just represents a sinusoidally oscillating input voltage. And we expect the voltage across our resistor to have some amplitude. It's going to be oscillating at the same frequency, but it may be shifted in phase relative to the input voltage. So to analyze this circuit, we could look at the current I that flows through the capacitor and resistor, and that's going to be equal to whatever the input voltage is divided by the net impedance of the series combination of the capacitor and resistor. And so this impedance of the capacitor is 1 over j omega c, and then we add to that the impedance of the resistor, which is just R. Written over a common denominator, this is equivalent to 1 plus j omega RC over j omega c. Okay, so the current then is going to be the input voltage divided by this impedance, which is Vn times j omega c divided by 1 plus j omega RC. We can multiply the top and bottom of this equation by the complex conjugate of the denominator, and that will remove any complex numbers from the denominator of this expression. And if we do that, we get V in j omega c 1 minus j omega RC divided by 1 plus omega RC squared. Okay, I'm just going to rewrite this in a slightly different way. I'll distribute the j, and I'm going to multiply and divide by R such that Vn could be written as, the current could be written as Vn divided by R times omega RC. And then let's see, we're going to have j times j is minus 1, and there's already a negative in there, so we're going to get a plus omega RC and then a plus j. And in the denominator, we have 1 plus omega RC squared. Okay, so there's our current. You can see already it's a complex number. If we wanted to then calculate the voltage across our resistor, we would just multiply the current by R, and we're left with V in omega RC plus J divided by 1 plus omega RC squared. Okay, and so that's an expression for the voltage across the resistor. It's a complex number, and so we're going to try to interpret or remind ourselves what is the meaning of quantity when it's complex. So to do that, I'm going to go back and I'm going to say, remember we expressed the voltage across the resistor as some amplitude e to the j omega t plus phi, and the input voltage as some amplitude e to the j omega t. So I'm going to substitute those expressions into here, and so we'll have that the voltage of the resistor is an amplitude e to the j omega t, and I'm going to write this as a product of exponentials, is equal to the input voltage, which is an amplitude e to the j omega t, and then we have omega RC plus j 1 plus omega RC squared. Okay, so a nice thing happens. The reason that we wrote our signals as complex exponentials is because we can just cancel this factor of e to the j omega t. And so now we have an expression that includes just the amplitudes of our signals, and in the case of the resistor voltage, a phase factor, and it looks like this. Okay, so now what we're going to do is we're going to make use of Euler's equation. So let's remind ourselves what Euler's equation was, and it's e to the j phi is equivalent to cos phi plus j sine of phi. Okay, so that means what we have is VR cos phi plus j VR sine of phi is equal to V naught omega RC plus j over 1 plus omega RC squared. Okay, so what we're going to do is we're going to take the real components and equate them, and we'll take the imaginary components, things multiplying j, and equate them. And so we'll end up with two equations, and that's going to be convenient because we're going to have two unknowns. Our unknowns are the amplitude of the resistor voltage and the phase of that voltage. So our first equation, equating the real parts, is that VR cos phi is equal to, okay, so what are the real parts of the right-hand side of this equation? So it's going to be V naught omega RC squared 1 plus omega RC squared. And if we take the imaginary part, so on the left-hand side, VR sine phi is equal to, let's see, everything that multiplies j is just V naught omega RC divided by 1 plus omega RC squared. So what I'm going to do is I'm going to call this real part of our equation x, and I'm going to call the imaginary part y. That's nice because if we calculate this ratio, say y over x, that's going to be VR sine phi divided by VR cos phi, and so that's just going to be tan of phi. And taking this ratio of these expressions that we have in terms of omega RC and V naught, this would just evaluate to 1 over omega RC. And so now what we have is that the phase of our resistor voltage relative to the input voltage is the inverse tangent of 1 over omega RC. Okay, and so that's one expression. All right. The next thing we could do is we could evaluate x squared plus y squared and ultimately take the square root of that. If we look here, x squared is going to be VR squared cos squared phi. Y squared is going to be VR squared sine squared phi. So we'll get a cos squared plus a sine squared, which is going to be 1. And so it's just going to be equal to the amplitude of our resistor voltage. I'll leave it to you to verify, but if you work this out, the amplitude of our resistor voltage would be equal to the amplitude of the input times omega RC divided by the square root of 1 plus omega RC squared. Okay, and so there's our expression for the amplitude. So if we look at this expression, if we went to really high frequency, in the denominator, the omega RC squared is going to dominate the 1. And so what we would end up with is omega RC in the numerator divided by omega RC in the denominator, and the resistor voltage would be equal to, the resistor voltage amplitude would be equal to the amplitude of the input at high frequency. If we go to low frequency, the 1 dominates the omega RC squared in the denominator, and we end up with V naught times omega RC. But at low frequency, the omega RC is very small, and so we have a small amplitude across voltage. We have a voltage across the resistor with a small amplitude at low frequency. And so this is the circuit that we analyzed is a high-pass filter. It attenuates signals at low frequencies and passes them at high frequencies. So let's look at the phase again. So let's think about the phase and try to interpret what does a complex quantity really indicate. So tan phi equals y over x. So let's suppose if y was equal to 0, so that our signal, in our case the voltage across the resistor, is purely real, then tan of phi is equal to 0. If we were to make a plot of the inverse tan or the arctan, so here's y over x, and here on our vertical axis is the inverse tangent of y over x. What that looks like is it asymptotically approaches pi by 2 at high values of y over x, and it approaches minus pi by 2 at large negative values, and it goes through 0 here. So if y is equal to 0, then tan phi is equal to 0, such that phi is equal to the inverse tan of 0, which is equal to 0. So a purely real signal then means that there's no phase shift of your output relative to the input. So a real signal means that the output is in phase with the input. Of course, the flip side of that is a complex signal indicates a phase shift. A phase shift of the output relative to the input. Okay, so how does this tie into lock-in detection? So a lock-in detector is able to measure the real and imaginary components of small AC signals when the signal frequency is known. Okay, and so if we measure those real and imaginary components, say x and y, so if x and y are known from our lock-in detection measurement, we can calculate the amplitude and phase of the signal. And so as we saw, the amplitude is going to be the square root of x squared plus y squared, and the phase, or that's right, the tan of the phase is going to be y divided by x. Okay, and so what we want to work out is how do we use a lock-in detector to measure x and y. So how is a lock-in detector, or let's say how does a lock-in detector determine x and y? Okay, good. So what we need to know is that lock-in detectors have two inputs. One of the inputs is the signal that you're trying to detect, and maybe that input also includes a whole bunch of noise that you are not interested in. And so here's a picture of our lock-in detector, and here's our signal input. So signal and possibly plus noise input. Okay, I mean, I said possibly plus noise. There's always going to be some noise. This is possibly plus a lot of noise. And then it has a second input, which is going to be our reference input. So our reference input is going to be, let's say, VR. It's going to have some amplitude. I'll say call it AR. And it has some frequency, omega RT, plus some phase. Okay. And then our signal input. So there may be some noise, but the signal that we're actually trying to detect is going to be some amplitude AS. Oh, sorry. I wrote my reference signal wrong, right? So it's an amplitude, and then it oscillates at frequency omega R. And then we have times T and plus a phase theta. So for our sample, we have an amplitude AS, and it's oscillating at potentially a different frequency. Okay, so omega S and times T, and maybe it has a different phase phi. So the goal is the following. Determine the amplitude and phase of the signal of interest when the reference input is known. So i.e., we know in advance the amplitude of the reference signal and the phase of the reference signal, and in fact, I guess, the frequency of the reference signal. Okay, so we'll assume that everything about the reference is known. That makes sense because that's generally the signal that's being used to stimulate or to drive our apparatus, and then we're trying to look for some response. So how is this done? How does the lock-end achieve this goal? So there's a few steps. The first step is to multiply the reference and input signals together. So internally, the lock-in detector multiplies the two signals. And so let's say after the multiplication, we have some output. I'm going to call it V out. It doesn't really make sense. It doesn't have units of voltage, right? Because we're multiplying two voltages together. But just for the sake of these notes, we have some output signal that is generated by multiplying our two voltages, our reference voltage and our signal voltage. Okay, and so when we take that product, we get the product of the two amplitudes, and then we have a product of sinusoidal functions, the reference one and the signal one. So via some trig identities, you could confirm that we could rewrite this as the product of the amplitudes divided by 2 times cos. So it's going to be omega st plus phi, that's the signal part, minus omega rt minus theta, that's the reference part, and then it's minus cos omega st plus phi, and then it's going to be plus omega rt plus theta. Okay, I'm going to rewrite that in a slightly different way. So I'm going to write that as ASAR over 2, and then we'll put a curly brace, then we'll have cos. So the first cosine is a difference in the frequencies and phases. So I'm going to write this as omega s minus omega rt plus phi minus theta. And then the second term is minus cos, and that one has the sum of the frequencies and phases. So cos omega s plus omega r times t plus phi plus theta. Okay, so there it is. That's the product of our two inputs. Notice that there's two terms here, obviously. One term is a sum of frequencies, and so this is like a high frequency term. And then one term is like a difference in frequencies, and so this is a low frequency term. So the next step is to take this product signal and pass it through a low-pass filter. And the purpose of this low-pass filter is just to get rid of the high-frequency term. So next, the multiplied signal is passed through a low pass filter, which removes the high frequency term. So the high frequency cos omega s plus omega r times t term. Okay, so after that, we have what we called V out. Maybe that's, we'll say after it's been filtered, that's V out prime. So after the filtering, we just have the low frequency difference term. So this is omega s minus omega r times t plus phi minus theta. Okay. So what we're going to do next is we're going to take this filtered difference term and we're going to average it over a long time. So the filtered signal V out prime is then averaged over a long time. And so, I mean, you can see this V out prime is just a cosine function, and a cosine function is half the time positive and half the time negative, and as long as we average over a time that is like many periods of the omega s minus omega r signal, then the V out prime is just going to average to 0. So if Vs is not equal to if omega s is not equal to omega r, then the average of V out prime is equal to 0. And this is really the essence to lock-in detection, because what it tells us is that the lock-in detector is blind to any signals that is not equal to the reference frequency. So the lock-in detector is blind to input signals with frequencies different than omega r. So we only get a non-zero average when the signal of interest is at the same frequency as the reference signal. We only get non-zero averages when omega s is equal to omega r. Okay, so in that case, so my notation that I'm going to use is we have V out was the product of the signals, V out prime was the product of the signals after the high pass filter. Inside these angle brackets means that that's a time average. And now I'm going to say, if we look at only the case where omega s is equal to omega r, what is that average going to be? Well, if omega s is equal to omega r, then we have the cos of 0 times t plus phi minus theta times the things out front. So we're going to have the product of the amplitudes divided by 2, and then we have the cos of phi minus theta. Okay, I'm going to call that equation star. I think we'll come back to it. And so that's quite good, except we still have two unknowns. So in star, we still have two unknowns. And our unknowns, remember, are we don't know the amplitude of the signal, and we don't know the phase of our signal. We know the reference amplitude and the reference phase. So we have two unknowns and only one equation. And so we can't independently solve for either the amplitude or the phase. So we need another step, and so I think we're on step 4. Step 4. So to establish two equations and two unknowns, we're going to take advantage of the fact that the reference signal is something under our control, and so we can manipulate it. Specifically, we can manipulate its phase, theta. So first, in part A, we set theta equal to 0, and if we do that, so now my notation's getting messy, but hopefully it's clear. We have the product of the signals after filtering, after averaging, considering only the case when the signal frequency is equal to the reference frequency, and where we've set the reference phase equal to 0, then what we would have is just theta equals 0 here, and so we have the product of amplitudes divided by 2 times cos phi. And so that's going to be equal to AS AR divided by 2 cos phi. And so what I'm going to do is I'm going to rewrite this as AR over 2 times AS cos phi, and I'm going to define that as AR over 2 times X, so that when we set theta equal to 0, what our lock-in detector is going to be able to tell us is the value of X, and that's equal to AS cos phi. And the way that the lock-in detector would actually calculate that is it would take advantage of the known amplitude of the reference signal, and it would use what it's calculated in this way. And so here's one of our first really important results. Okay. So we need two equations. We still have only one, and this one equation is used to establish this value of X that we're going to use. In the second equation, instead of setting the reference phase equal to 0, we're going to set the reference phase equal to pi by 2. And if we do that, we get V out prime omega s minus equals omega r. The reference phase is set to pi by 2, and that's going to be equal to AS AR over 2 cos of phi, and instead of 0, we have minus pi by 2 for the minus theta part of that. But cos of phi minus pi by 2 is the same as sine of phi. And so we could write this as AR over 2 times AS sine phi, which we're going to define as AR over 2 times Y. And so therefore, the other thing that the lock-in detector is going to tell us is after adjusting the reference phase by 90 degrees, we get that Y is AS sine phi, which the lock-in detector calculates using the known amplitude of the reference signal and this average product of the input and the reference when the frequencies are matched. And so here's our second equation. So the lock-in detector is able to accurately measure X equals AS cos phi and Y equals AS sine phi when omega s is equal to omega r. The signal of interest has the same frequency as the reference signal. So with these values, or let's say with x and y known, we can calculate the signal amplitude as x squared plus y squared over the square root, and the phase tan phi is equal to y over x. And then of course this is completely analogous to what we did using the RC circuit example, where we calculated the real and imaginary components of the voltage across the resistor, and then we were able to use those to determine the amplitude and phase. And so the lock-in detector is doing that kind of calculation for us. And so now we know the amplitude and phase of our signal. Okay, so that's where I'm going to stop for now, and in the next video what we'll start to think about is how well does the lock-in detector discriminate between a signal at some frequency omega s and a signal at a reference signal at frequency omega r. Or in other words, if omega s is very close to but not exactly equal to omega r, what happens? So how close in frequency do you need to be in order for the lock-in detector to extract the signal that you are interested in? All right, thank you very much.